0 of 8x over 3 sine x minus x. Okie dokie. What do you think? It is definitely 0 over 0 if you plug it in, so we need some kind of simplification. Now in my head, I haven't done this yet, but in my, at least not in years, in my head, I'm thinking I have x's and sine x's, so I'm thinking of my special limit. Okay. So what you might try to do, it's not exactly in the form of the special limit right now, right? But one thing you could try to do is divide everything by sine x. Because if I divide everything by sine x,
wow. Makes me feel like I'm asleep or
then this x over sine x is going to be 1 when I do my limit. This x over sine x is going to be 1. These sine x's are going to cancel and leave you with 3. So it should equal. So this is 8x over sine x over 3 minus x over sine x. And then, right, so each one of these, the 8's a constant multiple. You can pull it out front, you don't have to worry about it. X over sine x, this guy goes straight to 1. This guy goes straight to 1. So you get 8 over 3 minus 1. Because you're going to 0, right? You can only use this if you're going to 0. 8 over 2 is 4.
I didn't know you could think that.
That was tricky. I'm a tricky person.
Well, I'm glad it was in the review, not just in the test. You see it for the first
Yeah, if
time.
I just gave this to you on the test, then without showing it to you on the review, you wouldn't have had a chance. See how nice I am? I like that logic. That's good logic. What else? I know, it's those fractions, right?
Yeah.
You ruin everything. How much easier would life be if there were no fractions? Then you couldn't have a slice of pizza. You'd either have to eat the whole pizza or no pizza at all. So the limit as x goes to infinity, 2x to the 5/3 minus x to the 1/3, 7. So what happens when you plug in the infinity here? Right. On top, you're going to get x to the anything is going to go to infinity, x to a positive exponent. So this is going to infinity. This is going to a smaller infinity, because this is a smaller exponent. So this top ends up being infinity. The bottom ends up being infinity too, because you're just adding them. So this is indeterminate. So when you get infinity over infinity like this, you divide. What are you going to divide by? The bigger exponent. So I guess you have to decide whether.
5/3.
Yeah, I got to decide whether 5/3 or 8/5 is bigger. 5/3 is like what? 1 2/3, so 1.6666 repeating. 8/5 is about 1.6, I think. You divide it out and get a decimal. So this one's bigger. There's a lot of ways to do it, but you get a decimal real quick. So we'll divide by x to the 5/3. Let me go ahead and write this. Let me write this root as 1/2. 1/2 power. Everything max for 5/3. If you were really gonna simplify this, you'd have to do 8/5 minus 5/3 here. You'd have to do 1 minus, or 5/3 minus 1, and then you'd have to do 1/2 minus 5/3. But do you see what's gonna happen without me doing all that work?
It's just going to go to 0.
Right, 5/3 is bigger, the denominator is bigger, so this is gonna end up having an x on the bottom. So this is going to 0. 5/3 is bigger than 1, so this is going to have 2/3 x's on the bottom. This is going to 0. 5/3 is bigger than 1/2, this is going to 0.
So it's 2 over 0.
Yep, 5/3 is bigger than 1/3, this is going to 0. 5/3 is, well, this is a constant, it's going to 0. These guys go to 1, so you get 2 over 0. That's your form here. So it kind of just comes down to what happens when you plug in a large positive number. Very large actually, but the bottom when you plug in a positive number is going to be positive because it's all plus signs. What about the top? Still positive because this guy's way bigger than this guy, right? This is 1/3 to the 5th power. So if you plug in 100, this 5th power is going to take over. And then the minus is going to matter. So you go to positive infinity. Pay particular attention to whether you're going to 0, whether you're going to infinity, or whether you're going to a constant, because that's gonna tell you which rules you can use and which method to use.
14.
Oh yeah. 14. 14 has a natural log in it.
Graph's like a square root going down, right?
Yeah, it's kind of like a square root, but it goes down to negative infinity, so it's a swoop. So kind of the prerequisite knowledge here. Your natural log of x graph looks like this. But if you have a scientific calculator, you don't actually even really need to memorize this graph, right? Because what's going to happen here is you do need to know a little bit, right? Because when you try to plug in 3, what happens? It's undefined. Limit as t goes to 3 from the positive, natural log of t minus 3. If you try to plug in 3, you get natural log of 0, which is undefined. Even your calculator will tell you that. I mean, if you plug in natural log of 0, it'll say error or something. Okay. So then what you need to decide, well, hopefully if you have this image in your head, then you just need to decide whether you're going to positive infinity or negative infinity or what's going on with the graph. What's it look like? What do you think you're going to go to in this graph here? Negative infinity. What does this do? What does this minus 3 do to my graph?
So the horizontal shift.
So if this is natural log of x, 1, 2, 3, I'm going going to just shift everything over 3. So then it's clear that as t or x goes to 3 from the positive side, my function's going down to negative. Worst comes to worst on this, make a table. I'll give you some credit if you do, 3.1, 3.01, 3.001. I'll give you some credit for that. And you'll just see that these get more and more negative.
You know, so many tables.
Be careful on the test. If I will say, evaluate the limit algebraically, or maybe even I'll say evaluate the limit, do not use a table. So if I tell you do not use a table, and you don't show me how you did it, I'm not going to give you credit. Okay? So, because you can just plug all these in your calculator, probably, there are a lot of them. If I don't say do not use a table, what else?
Well, you only get partial credit if you do.
If you use a table?
Yeah.
And I say do not use a table?
No. But if you don't say anything.
If I don't say it, then yeah, that's fine. But show me your table so I know that you don't just put an answer that you didn't just copy.
You get like 100% credit?
Yeah. If it doesn't say do not use a table, yeah. It's going to say, I'm just going to write that on my phone. At the top, never use a table.
Ever.
No. You're going to have to eat on your lap.
Say it on the first one. Use a table.
So you guys will blow up. So, anything else? I'm sure you haven't looked at this much. But,
Oh, I had a question. For like 29, as far as like, is that what we're going to be looking at? Kind of simple like that, or are we going to be?
well, I don't think this is too simple. I think this is okay.
It's like two horizontal lines. You just have to get the point.
Yeah, but it actually doesn't matter what I put. I mean, I can put anything on the top and anything on the bottom. The process is still the same. Like, how do you find, for number 29, for what values of A and B is this function continuous everywhere? How's this work?
It would be -1, -2, and then 0.31. Well, yeah, you'd find a line, but that's
Let's go through the logic here so you can do it no matter what functions I put, whether the lines or not.
yeah.
Oh, minus, thank you. So, as far as intuition goes, like you guys are thinking, we have a graph that's y equals -2 somewhere, right, after, to the left of x equals -1. And then to the right of x equals 1, we have 3. And then in between we have ax minus b, which is some sort of line. Who knows what line it is? And so what we need to do is figure out exactly what slope and what y-intercept I should use so that this line falls right on top on both sides, right? We need to, continuous everywhere means I can't have any jumps or breaks or holes anywhere. So I have to pick A and B so these match up. But what's the calculus way of saying something's continuous, or the calculus way of saying that these match up? Right, so you need the limit to equal the function value. And because we have two different functions on each side, what you really want for continuity at -1 is that the limit as x goes to -1 from the left equals the limit as x goes to -1 from the right equals f of -1. The limit equals the function value. That's what you want. And no matter what function I put here or here, this is what you're going to want. And I could change this to any polynomial, and this is what you're going to want. What does evaluating this limit come down to? The limit as x goes to -1 from the left side. It's -2 because you just look at this part of the piecewise function and plug in -1. If I change this to say -2x squared plus x, let's do plus 3x. Then what does this limit become? Then you plug -1 in for x. Right? So you get -1 squared, which is 1. So -2 times plus -3 is -5. So if there's a more complicated function here, you still calculate this limit, but what you have to do is actually plug in the -1. But in this particular case, because it's just a constant, this limit is -2. The limit from the other side is what?
Should be
The limit from the right, you take x to -1 on this guy. Right? Because this, from the right of -1, you need to be greater than -1. So if I plug -1 in here, what do I get? And then I still have to be sure that this limit equals the function value. The function value is actually, what's f of -1 here? That one's -2 because you look where the equal sign is. So this is kind of the calculus behind figuring out whether it's continuous at -1.
But the last one has the equal sign too.
Yes?
No, the x is
If
greater
x
than 1.
or bigger
For
than
3.
1.
Oh, this. Thank you. Right here you're saying?
Yeah, it wouldn't change it?
Not for this part because this
Oh,
is
it's
-1. Yeah, but when I get to the 1, it would. In fact, that's a good point. So all this tells me is, whatever I do here, I need to have -2 equal to -a minus b. If I make that happen, that'll make me continuous at -1.
Then just do y1 minus y2.
Well, then I have to make sure I'm continuous at 1 as well, because I have to be continuous everywhere. So I get another equation when I check what happens as x goes to 1. Right, because as x goes to 1, everything has to match up. But the limit as x goes to 1 from the negative side is what? Focusing on 1 from the negative side, plug 1 in here. A minus b. Limit as x goes to 1 from the positive side. So this is the positive side of 1. 3. Finally, f of 1, this is where my equal to is, so it'll be 3. So then I have to make these equal, so I have to solve this. But now I have a system of equations, right? I need a minus b to equal 3, and I need -2 to equal -a minus b. So, how do you solve that system of equations?
You put one on like A equals 3 plus B, and then
Yeah, you can
replace it with
substitute.
the other one.
You can substitute, or you can add, right? The other method is to add the equations. If you add the equations, in this case, the a's cancel and you get negative 2b equals 1. So b equals negative a half. And then if you plug in negative a half for b, a minus negative a half equals 3. So a plus 1/2 equals 3. Did I make a mistake?
Did you say?
Every problem in calculus is long. So let's see, 3/2 is 6/2 minus a half is 5/2.
So, would it be worth, would we get points knocked off if we did, since it would be 3, 1 for the point on the right, and it would be -2, negative, or it would be -1, -2 on the left, and then if we just did like y2 minus y1.
I won't give you a line.
Wait, but wouldn't we still have the point anyway?
I won't give you a line here, so you can't use slope. I'll just give you a problem.
I don't understand. Like,
Basically, you gotta make it way harder.
No. Then it's not 1, right? Then it's this. But everything's still the same. You just have to plug in -1 here instead. Plug in -1 there and you get a minus b. Plug in 1 here and you get a minus b. And then you can solve. So, will you get points marked off if I give you a line? No, because that's perfectly legit. But be aware that if I don't give you a line, there's going to be a slightly more calculus-y way to do it.
yeah, that's my question, because if it was simple, then you could give us a line on the test. I didn't think.
Yeah, so I'm showing you kind of the legit way to do it. One question, if I take this off here, last question before I let you go. If I, remember how I had this off? Next, let's go back to the line for a second. What does that change about the answer to this question?
We can use either or. I'm just kidding.
Nothing, really.
So I'm supposed to find a and b so that this is continuous everywhere. But remember, you have to have the limit equal to the function value. What's f of 1?
Undefined?
Fine. So no matter how I play my game with this line, this guy's undefined. Right? So this is a hole here. So I'll never be continuous at 1. There's no a and b that'll work because of this hole. So there'd be no solution to the problem if I